Well, hello and welcome, guys. Hope everybody's doing all right. We're getting down to the last little bit of the class, only a few sections to go. So today's announcements are so the first announcement is just another reminder that our final exam is coming up fairly soon. It's 2 weeks from last Monday? It's Monday, May 4th, 12 to 9 a.m. The exam is cumulative, which means it covers everything in the course. The only thing I'm leaving out is the epsilon delta stuff from section 1.7. That won't be on the exam. We probably also won't get to section 3.8, which we never covered, so that one won't be on there either. Then you should have received an email about, a half hour ago for quiz 9. That'll be due at 5 p.m. in Sakai, so make sure you get that done. And then we have our usual homework due tonight. Okay, there's only 3 more homeworks left, so you're getting down there. You can just stick it out a little bit longer. Yeah, but before we get started, any other questions? So there'll be one more quiz after today. There'll be one next Monday. But it won't be that bad of a quiz. Once you see it, you realize it's not that bad next week. I mean, there will be some math and some not math, just like this week. But yeah, quiz today and quiz next Monday. Homework tonight, Sunday, and then next Wednesday there will be one. Oh, so yeah, I should add, I'm also planning to exclude section 5.1. We're going to cover it probably either on Friday or next Monday, but just because it's so close to the final exam and because it's not like vital knowledge, I'm not going to leave that. I'm not going to test on it. So you can, there will be homework on it, but I'm not going to put it on the exam. Any other questions? Okay, well, let's move right along. So we're hitting section 4.4 today. So this is, I think we're actually mixing sections a little bit here, but what we're talking about today is indefinite integrals and the net change theorem. Okay, so kind of 2 main things we want to get through today are those 2 things, indefinite integrals and net change, that idea, which we already kind of talked about last time, but we're going to go into it in more detail. So, okay, let's sort of think back to what we've done so far. So up till now, we've spent a long time sort of concentrating on the definite integral, right? So the definite integral is this symbol that calculates the area between a function and the x-axis over a certain interval. And we use this integral symbol. And then we learned by the fundamental theorem of calculus that one way to calculate this is to find an antiderivative of whatever's inside the integral and plug in the bounds. Okay. And so yeah, f is an antiderivative. But a lot of times, like, we get sick of saying the word antiderivative, right? It's a long word. I get sick of writing it, repeatedly. So what we do instead is we introduce another notation Because another way you could think of, so new notation. Let me just tell you the definition first. The indefinite integral. So this one was definite, and this one's indefinite. The indefinite integral of a function f is defined to be the collection. So we're defining indefinite integral, and it's going to be the collection of all antiderivatives. So does anybody remember what name we had for that? We had another name for this, for the collection of all antiderivatives. What else did we call that? Nobody? So the collection of all antiderivatives, if I give you a function f and I ask you to find all antiderivatives, that's what we call the most general antiderivative. So this is just a notation for the most general antiderivative. It's denoted with an integral sign, but now we don't put bounds. Okay, so so that's the definition. Let me point some stuff out. So if I do take an indefinite integral, it's basically just a notation for saying find the most general antiderivative. So all you have to do is you find an antiderivative, and then you add a constant, right? Because a constant tells you that there's more than one for each different c value, and so this gives you all of them for all the different c's. Of little f. Okay, so now why do we use the terms definite versus indefinite? Well, if something's definite, that means it has a particular value. Like something is defined, it means it's equal to one particular thing. It's definite. It's definitely equal to something, right? And so when you take a definite integral, it's equal to the number that is the area. It's equal to an exact number, right? So it's equal to some number that gives the exact area. But in an indefinite integral, it's sort of indefinite, or not quite defined, because we have this plus c, right? Which means we know the antiderivative only, like, we don't know exactly what the antiderivative is because there's many of them, right? So that's why it's indefinite. Because it's not quite perfectly defined because there's many antiderivatives. Okay, and so yeah, the way you tell them apart is, do they have bounds or not? If they have bounds, it's a definite integral, and it's going to give an area. If there's no bounds, like here, then it's just asking you to find the most general antiderivative. So, this thing's code for the. And why do we do this? Why do we use this other notation? Right, you'll notice like a lot of things in this class are just like 5 different ways to say the same thing. And it's because, notation is a useful way to organize thinking. And so sometimes one thing is more convenient than another. And so why do we use this integral notation for antiderivative? Well, part of it is because we get sick of writing antiderivative and it's easier to just write a symbol. And the other thing is it's related to this part up here. So when we did this part up here, another way to write this would have been is we could have found the most general antiderivative, which is now just the indefinite integral. And then we have to just plug in from A to B. Right, where this bar is the evaluation bar, means to plug in, right? So it's just saying, the definite integral is the indefinite integral where you kind of just take the bounds and the evaluation bounds and you stick them on there, right? So it's kind of the one step simpler in the notation, right? Okay, so that's what an indefinite integral is. It's not anything really new for us, right? It's just find the most general antiderivative, right? Okay, so not too bad. Let's do some quick examples. So example, let's compute what's the indefinite integral of secant squared. Well, we just find an antiderivative. So by now we should be able to tell that an antiderivative of this is just tangent of t, because its derivative is secant squared. But to make it the most general antiderivative, we put our plus c in to say, well, this is all possible antiderivatives. There's one for each value of c. And that's really all there is to it, right? So it's sort of, when you're doing a definite integral, you first basically take the indefinite integral and then you plug in, right? Let's do another one. Let's say, what's the indefinite integral of, say, x cubed minus 3x dx? So if you just look at this for the first time, you may think, well, I don't actually know what the antiderivative of this formula is. And so to put it into a more recognizable form, what I would do is I would break up the fraction, right? I would break it up like this. Right? You can break fractions up in the numerator, not the denominator, but, and then we can think about this in terms of powers. And it's important to note that indefinite integrals follow all the same rules as the definite integrals, right? So you can still break them up into smaller integrals if you would like. So this would be x to the cube times, now 1 over root x is the same as x to the minus 1/2. So we could split this up into two integrals if we wanted to make our lives a little easier. Okay. And if we combine the powers then, so it'd be what, 6 5/2 x to the 5/2 minus 3x to the 1/2. Oops, I forgot an integral sign here, integral. And so when you take the antiderivative, right, you use like the inverse power rule, which says you would add 1 to the power. That would go up to 7/2. Then I divide by the new power. So that would be dividing by 7/2, which is the same as multiplying by 2 over 7. Minus, now this one would go up to what, 3/2 times 2/3. Then we have the extra 3 out front. And you may be worried that like you get a plus c from each of these integrals. And that's sort of true. Like you could think of there being like a c1 plus a c2, one from each integral. But because, because these constants are not fixed numbers. They're just standing for an unknown constant. So these two numbers could in principle be anything, right? So if there's two things that could in principle be anything, I can always combine them into one thing that could be anything, right? So we typically just always leave one constant. Okay, unless there's some, yeah, because, yeah. And you didn't have to actually split this up into two integrals. You could have just kept it all inside of one integral and found the antiderivative just the old way as well. So yeah, so that'd be the answer. You just find the antiderivative, tack on plus c. That's all there really is to an indefinite integral. The hard part of it is finding the antiderivative. Okay, so questions about this so far? Okay, so that was sort of the indefinite integral part. Let's talk now about what your book calls the net change theorem. I don't typically give it a name at all. Well, I mean, it already has a name is my point. This is just another term for the fundamental theorem of calculus. So this is really just a slightly different way of writing exactly the fundamental theorem of calculus, right? So remember, fundamental theorem of calculus, I think which part? Part 2, I think we called it. Said if I take an integral of something, so here I'm putting a derivative in here. So that's really the only change we're making is we're going to think of the thing we're integrating as something's derivative already. Well, the fundamental theorem of calculus would say that to calculate this, I would find an antiderivative of this. So I need something whose derivative is f prime. Well, that's clearly just going to be capital F itself, right? The antiderivative of a derivative is just itself. So this would be just f of b minus f of a. Okay, so this is the net change theorem. But I just, it's useful to think about this way because really what this is saying is saying that the integral of a rate of change, so something that involves a rate, over some time period or distance or something, that is equal to the net change and I guess what I've been calling the original function, the not rate one. So, there's an f prime on the left side, but there's no prime on the right, right? The original function. So this is why we call it the net change theorem, is because it tells us how, if we want to know how much a quantity changed by, that would be the right-hand side. One thing we can do is we can just calculate the definite integral of the, sorry, there's a dog barking, rate of change of the function between a and b. Okay. And this is, really quite often, this is how it shows up in applications. So that's why we want to, it's important to think about this. So yeah, kind of one of the most common, at least, when we teach this, is the way this shows up is in terms of position and velocity. So if v of t is the velocity, and so, yeah, okay, of an object, and S of t is its position. So let's give these some units. Velocity is, let's say that's in miles per hour or something, time or distance over time. And let's say the position then would just be in miles. In miles. Then if I took the definite integral between two time values, so if I integrate the velocity, what do we think should happen? Well, what do we know about the relationship between position and velocity? We know that if we take the derivative of position, that's equal to velocity, right? So really, this thing in here is S prime of t. It's the rate of change of position. So that means if we integrate the rate of change of position, it should tell us about the change in position, right? Okay. And so that's indeed exactly what happens. And we, just to have a standard term for this, I'm going to give this S of b minus S of a the term the total displacement. Because there's sort of two related ideas that are close but different. So displacement means how far did it end up from where it started? Okay, and so yeah, it's where it was at time b minus where it was at time a. It's how far it moved if you only know those two moments in time. Okay, and maybe it's worth pointing out that it's useful to remember, like, if you think about units, so remember, if I took, if f has, so if I start with the function f of x, then if I take the derivative of f, this has units. It was the units of f itself divided by the units of the input, right? So there we divided by units, right? Because f has units of f. If you take an integral, well, integrals are supposed to be essentially the opposite of taking a derivative, so you would think that instead of dividing by the input units, you would multiply, and that's exactly what happens. So whenever you integrate, as units, let's see, what's the best way to write this? Units of f times units of x. So it multiplies by an additional units of the input. Right, because if you think about, sorry, maybe I should leave that up for a minute. So if you think about our example, when we took an integral of a velocity, that was distance per time. When we integrated that, it went to just distance, right? And that's basically the same as multiplying by the units of time, right? Distance over time times time is just distance, right? So that's basically what happened here, right? V of t had, distance per time, and then this side had distance per time times time, which is just distance. It's a difference of distances, but it's still a distance, right? Okay. So that's, this is what we're going to call the total displacement. So basically, this is a formula for the total displacement, if you want to think about it like that. because that is something I might ask you about, is to find the total displacement. A sort of related concept is, what if I instead ask about this quantity? So now I'm putting absolute values around the velocity. So this we're going to give a different term. This gives the, what we'll call the total distance traveled. Okay, and so the idea here is, you know, in this class we typically always just imagine that we have an object that's moving in a straight line. It doesn't strictly have to be true, but it makes it easiest to visualize. And so you should imagine, you have an object that starts somewhere. Maybe it moves along, but then maybe it stops and turns around. And then maybe it turns around again and it goes the other way for a little bit. And it can do that, any number of times depending on the situation, right? Like maybe you had a biker that rode out a ways, then came back or something. So in the first situation, the total displacement, so, oops, would be, the object ended up here and it started here. So the total displacement would be this. That was the first idea. It's sort of ignoring that it, whatever happened in between. It just cares about where it started and where it ended. But if I put absolute values in here, it's saying, well, I treat any time I go backwards as if I'm going forwards. So it's saying, if I go this distance, and then I keep going forward, I would go this distance again, and then I would go all these distances. So if I add all these distances together, this is like the, if you imagine you were going on a bike ride and you went like a route like this would be like the actual distance you rode, right? So this is the total distance traveled. Like you traveled further than just the distance between where you started and where you ended up, right? You went back and forth a little bit in there. Okay, so that's the difference here. And the absolute values, help us here because it turns all these things that would be negative areas for the places where they're going backwards into positive areas. But it makes doing the integral a little trickier. Okay. So that's the concept. Let's see an example of this. Okay. So okay, so here's the situation. We have some object that moves in a straight line, and we're given its velocity. And we're going to work in units of meters per second here. And our first goal is going to be to find the total displacement between times 1 and times 4. And then our second one, I'll give us a bit of room down here, will be to find the total distance traveled over that same time period. Okay, so again, we're going to be looking for total distance traveled and these total displacements, and they're different concepts, right? Okay, so if you think about what we did above, the formula for total displacement is you just always integrate the velocity over your interval, right? Because that'll tell you the change in position, right? The integral of velocity is the net change in position. That's what we call total displacement. And so all you have to do here is you have to integrate from 1 to 4. And this will tell you, you know, s of 4 minus s of 1. But we don't actually care about what s of 4 and s of 1 are. We actually couldn't figure it out given the information. So we just crank it out. So remember, at this point, we're going to almost always do it, unless I specifically ask otherwise, using the fundamental theorem of calculus. So that means you take an antiderivative, and then you evaluate at your bounds. And what do you get? You get 4 cubed over 3 minus 16 over 2 minus 6. That would come from plugging in 4. Or sorry, I didn't take the correct antiderivative. It should be 6 times 4. Right, the antiderivative of 6 should be 6t minus, now we plug in 1, minus 6 times 1. And apparently if you do that all out, if I plugged it all in correctly, you should get minus 9 halves. So the negative sign would tell us that it ended up before where it started, right? You know, in these situations, you always sort of have, before you even start, whoever asked the problem has, you know, a direction that they're calling positive. So this object, after 4 seconds, ended up before where it started by minus 9 halves. And the units here, well, if we're integrating a velocity, that should tell us about a change in position. So that should have units of position, which should just be meters. Or you could think about it in terms like we did before, right? If we integrate velocity, that'll be the units of velocity, meters per second, times the units of the inputs, which is time. So meters per second times seconds is just meters. So that's the total displacement. Okay. Now the trickier one is, in my opinion, is the total distance traveled. Okay. Because remember, the formula for that is we have to put this pesky absolute value in there, right? To make sure that we count all the going back and forth. Because if you just integrate it all, you know, it sort of ignores the going back and forth. So, but we can start by writing that down, right? It'll be the integral from 1 to 4 of absolute value of v of t. So, you know, we don't really have a formula that just tells us how do we take an antiderivative of something that involves an absolute value. Well, by now you might be realizing that like whenever there's an absolute value involved, typically you have to do some sort of like piecewise process. You have to do it in pieces, right? Because an absolute value switches what it does based on whether the input is negative or positive, right? So you have to do one thing when it's positive and another thing when it's negative. That's usually the idea. And so here we have to decide, like, where is my function positive and negative? And then we're going to break it up into two pieces. So let's think about this part. So t squared minus t minus 6, if we factor that, that's what must be minus 3 and plus 2. Yep. So if we graph that, it means it's an upward facing parabola, and it passes through the x-axis at 3 and minus 2. So 3 minus 2, upward facing parabola. It probably doesn't have its min at 0. Okay. And so what we see here is, so this would be v of t without the absolute values, right? So this function is negative on this part, right? This is the part that's below the x-axis. So if we take an absolute value of v of t, well, on the positive parts, the absolute value doesn't do anything, so that part remains the same, right? So just imagine these are like, I'm drawing them a little bit off from each other just so you can see them. And then what it would do in the negative part is it would make everything that was negative the same thing but positive, right? It would switch this y value to its positive. And so what it does is it reflects it above the x-axis. Oh God. Something like this, right? So now it's a funny looking function. And the area we're trying to calculate is what? So this is absolute value of v of t. And the area we're trying to calculate is between 1 and 4. So let's mark those off. Okay, so 1 would be here somewhere. 4 is going to be over here somewhere. So we're looking for this area plus this area, right? So we see that they're both positives, right? In the other ones, we would have had a negative area and a positive area in the part A. Okay, so the trick here is whenever you're doing an integral that involves an absolute value, you basically break it into two pieces, or you break it into pieces wherever the sign switches, right? So between 1 and 3, it was negative, right? So that part gets one integral. But it was negative, right? It was negative there, so to make it positive, we switch it with a negative, right? Negative of a negative will be positive. Okay, so that'll give us the first area. That'll give us the area from here to from 1 to 3. Then to get the second area, we take the integral of just the regular function, right? Okay. So like, if area 1 is here and area 2 is here, right, this whole thing is area 1, this whole thing is area 2. So that's kind of the key point here, is whenever you have an integral of an absolute value, you just split it into pieces where it's positive or negative. And if you have a negative part, you switch it to being positive by adding an extra negative. And then once you've done that, there's no absolute values anymore. So you can just crank each one out, just like you did before. So this would be minus t cubed over 3 minus t squared over 2 minus 6t from 1 to 3 plus, and then we do it in the second integral, the same thing. You get t cubed over 3. Now from, oh, sorry, my bounds are all messed up. The first integral went from 1 to 3, then the second one should have gone from 3 to 4. Right, you should have the first bit and then the second bit. That makes more sense. Then you just throw everything in. It's a little bit tedious to plug everything in. 3 squared over 2. And you have to be careful with your negative signs, right? So there's like 3 layers of negatives here. Four cubed over 3 minus 4 squared over 2 minus. So that would be plugging 4 in, and then you have to plug 3 in. Minus okay, so you get this big long thing, right? And sometimes you'll see that a little bit of it cancels. Like you'll notice here that this term is the same as this term. But they're both negative, right? So it's really minus twice one of them. So you can do a little simplification sometimes. But often it's just, you can just plug it into a calculator, and I'll tell you if you do that here, what I got was 61 over 2. So it's important, if you ever get a negative answer when you're doing total distance traveled, then something went wrong, right? Because total distance traveled should always be a positive number because it's how far you went. You can't go a negative distance. You can end up at a negative position, but you can't go a negative total distance. Okay, so any questions about this? This can be kind of tricky your first few times. Oh, 61 over 6, actually. Okay, so here's another example. This is more of just an interpretation one. It says you know that there's a population of bees. It starts out with exactly 1,000 bees and increases at a rate of something that's only given as n prime of t, so it's the derivative of the number of bees. So it's a rate, keyword rate here, per week. So we're given the rate of bees per week. And then we're asked, what is this quantity 1,000 plus the integral from 0 to n prime, or from 0 to 15 of n prime, what does that represent? And so, in sort of words, 1,000 is what? It's the initial bee population. So what the population started as. And then what does the integral part represent? Well, if we're integrating a rate, that represents the net change, right? This is the net change in n, which would be the number of bees. So the net change in number of bees between 0 and 15. Now, 0 and 15, they're units of, or they're always have units of whatever the input is, right? So that would be weeks. Okay, so now if you think about adding these, so saying if I started with 1,000 bees and then I added to it the amount that the population changed by between 0 and 15 weeks, well, that would tell you what the population was 15 weeks later. So this altogether tells you the total bee population at t equals 15 weeks, right? So this is just an example that if you want to know like the exact value of an original function, you have to have an extra piece of information, right? Just if we just had the integral here, so if we covered up the 1,000, that would only tell us how much the population changed by, right? We didn't know what it started at, so we didn't know what it ended at, right? We just knew the change, right? And so if you want to end up knowing the original completely, you have to have like a starting or ending point, or even some point in the middle actually works as well. Okay. So that was just, thinking about what these things mean. Which other one should we do? Probably have time for one more. Okay, so as our last example for today, we imagine that there's being water pumped into a large tank, and we're given the rate at which the water is entering the tank. So it's basically we have that the water is entering at 30 liters per minute, and then whatever's pumping it in, it seems like it doesn't do it at a perfect 30 liters per minute. It has some little bit of oscillation. It goes up and down a little bit by this other amount, and we want to know exactly how much water has been added to the tank if we wait 30 minutes from t equals 0. And so if we ever want to know, so if we think about this, the rate, the R of t, what does that represent? That's water added to the tank per minute, right? Liters per minute. There's this amount of liters added every minute, and that amount is changing a little bit. And so that's the rate of change of the amount of water added, right? So if we want to know the net change in the amount of water added, we have to integrate this, right? So this is an example where you would integrate the rate over your time period, and that will give you the amount it's changed by. So you would just go ahead and crank that out. Here it's actually not a nice number. I don't think so. But we can at least go through the steps. So we would throw this function in there. Then we would just crank through the integral. So we would find the antiderivative, which is 30t. And then maybe it's useful to simplify this to be 1 over 50 cosine of t. Just distribute it to be 2 terms, plus 1 over 50. Now the antiderivative of cosine is sine. And the antiderivative of a number will just be that number times t. So that's our antiderivative. Then we have to plug in this from 0 to 30. If you do that, at 30, you get some number. But it's not a nice number, right? Because sine of 30 is not, it's got to be some irrational thing. But it's some number between 0 and 1, or between -1 and 1. So that would come from plugging in 30. And you should never, even if the bottom bound is 0, you should always just check what it gives, right? Here it turns out that it gives all zeros, but often it doesn't. So don't ever skip it. All right, you just get a bunch of zeros here though. And this is subtracted. So your answer just ends up being this part. Okay, and its units would be, because we integrated a rate that was liters per minute, we're going to be multiplying that by minutes, and so it'll end up with being liters. So this will be the amount of liters added. Liters of water added. Okay, you guys start to see the pattern here? Okay, then I'll let you go a little early so you have time to do your quiz if you have a busy day. But other than that, yeah, have a good day, and I'll see you on Friday.